Hi again, everyone. Hello from your favorite data science podcast. I hope it's your favorite. Welcome to season two of Chai Time Data Science. I took a long break. I'm sorry if I kept you waiting, but I'm really excited to kick off season two by interviewing Dr. Clair Sullivan, who's a graph data science advocate at Neo4j. She studied nuclear engineering, and in this episode, we talk about how she took up the challenge from a Nobel laureate and pursued engineering and later transitioned from academia to industry. We talk a lot about graphs, not the ones that we plot, but the graph data structure. Neo4j is based completely around graph data structures, and we talk about that ecosystem. This was recorded a while ago, so their conference Node 2021 was yet to happen. You can find the links to everything we discuss in the show notes. I also have one request for you all. If you've been enjoying this show, please let me know things you'd like to see or things changes you'd like to be made. Your feedback would really mean a lot. So please connect with me anywhere. Let me know if you like the podcast, things you don't like, things you'd like me to do better. I'd really be happy to work on them. Season two won't have the release pace as earlier, but I'll definitely make sure that I try to improve on things as you like them best. And without further ado, here's my conversation with Dr. Clair Sullivan from Neo4j, all about graphs and Neo4j. Enjoy the conversation. Thank you so much for joining me on the first episode, I think, of season two.
Thank you for having me.
So I have a lot of interesting stories about your background that I'd love to dive into. But the first one that I'm really curious about is your story of accepting a challenge to against a Nobel laureate who said some bad words around engineering. Could you tell us what that's about?
Yes, I will not name names, but this was when I was an undergraduate. I went to the University of Michigan, and in my undergraduate, I was a joint major in physics and astronomy. And this was in the physics department, and there was a Nobel laureate coming to speak on campus. So, of course, we all had to go to his talk. And the department decided, oh, well, the undergrads, they'll never get a chance to meet a Nobel laureate or have a conversation with him. So we should have a special event just for them. So they got us all together at one of the professors' houses, and we all sat in a circle with our little cans of Coke, and he was telling us his views on life, the universe, and everything. And somebody asked him what his view of intelligence was. And he said, this is a pyramid. Intelligence is a pyramid. And at the absolute pinnacle of the pyramid, you have the best of the best. You have the creme de la creme. You have the mathematician. This is science in its most pure form. And then he said, and then you have the next level below that, which is the theoretical physicist. And, these people are, of which he considered himself, and these people are brilliant minds, and they really work hand in hand with the mathematician. And then the next level below that, you have the experimental physicist. And what they do is in support of the theoretical physicist, and they're very smart people. And then the layer below that, you had the applied physicist, astrophysics, biophysics, things like this. And I was in astrophysics at the time, and they don't really have any business putting the word physics in their title, but we let it slide. And then at the bottom of the pyramid, you have the low of the low, the scum of the scum. No joke, he said this. The low of the low, the scum of the scum, you have the engineer. And in that moment, I said, okay, I'm going to be an engineer.
That's an awesome story. Uh, I've been told the same story in my undergrad as well. I wonder if there's a secret group where they decide on sharing the story everywhere.
It's funny because when I became an engineer, when I was in graduate school, there were some of the professors in my department who had, their PhDs in physics. And I said to them several times, I'm like, I'm not sure what to call myself. Am I an engineer? Am I a physicist? And the ones who had gotten their degrees in physics, they always said I was a physicist. And the engineers said I was an engineer. So I still don't know what to call myself.
I studied engineering. I don't know what to call myself either. But after that, you went on to study nuclear engineering. Very fascinating stuff. a lot of things I didn't understand. So if you could please help me understand it in simple terms, what were the things you were working on? Because it looked awfully similar to what we'd call data science today.
Yeah. And I mean, when I was in graduate school, this was the late 90s, and there was no term data science, big data, none of these things. Machine learning, maybe a few people were talking about that, but nothing major. And at the time, I liked building things. I liked working with my hands. I liked turning knobs in the lab and stuff like this. And I had decided I did not want to go to graduate school, actually. So I accepted a job with my undergrad in physics and astronomy. I accepted a job as a computer programmer, making an embarrassing low amount of money, basically the equivalent of a grad student who's on a fellowship. And those students don't make a lot of money. But I accepted this job, and then it was this strange circumstance of events where a professor in nuclear engineering had met me. I was part of an undergraduate research program, and the woman who ran that program found out I did not want to go to graduate school, and it was to encourage women and minorities to go to graduate school. So she said, "I want to introduce you to this professor, and she's in nuclear engineering." Okay, fine. And the professor said she could get me in, and maybe we could get some funding for it. And I said, oh, geez, nuclear engineering. I'm not a nuclear engineer. I'm an astrophysicist. What are we doing here? But it turned out, you're talking about the smallest things in the universe to the biggest things. But in fact, they actually behave in very similar ways. When I was an undergrad, I liked building things. I was building receivers for radio telescopes. And then I got to graduate school and I was building detectors for radiation. So nuclear engineering, people think of as, designing nuclear reactors and things like that, but it's really the application of nuclear physics. So I can use a neutron to split the atom, or I can measure neutrons. There are types of radiation that we can measure that are associated with the splitting of the atom and whatnot. There's natural radiation all around us. And so I got really involved in building detectors for that. And, it was just, okay, well, this is just going to be my thesis. And at that point, I was working with a man he was a brand new professor. And then September 11th, 2001 happened while I was in graduate school. And that was about a year before I graduated. And I mean, it was very impactful on me and obviously many other people. And I remember all of us were wandering around in this daze. We couldn't believe it. And I wandered to my professor's office, and he was Chinese and had been at Tiananmen Square, had experienced so many things in life for being so young. And I walked in and we were both just in this daze, and I just kind of flopped down in the chair in his office. And he said to me something that I'll never forget. He said, I write my proposals, my research proposals, and I always say that the work that we do could be used to fight nuclear terrorism. And until today, I had no idea what that meant. And that was very, very impactful for me. So I dedicated the first portion of my career to trying to fight nuclear terrorism. So
That's an
yep.
amazing story. And just curious, so were the seeds of data science, data analysis planted at that time? Because you were talking about measuring radiation, and it's not like, I would assume you're not putting on a suit and going into Chernobyl trying to measure the radiation. It's more in a computer.
I was.
Okay.
I did do work like that. But my first job after graduate school, again, this was a year after September 11th. And in the United States, they were looking for anybody who could do anything related to radiation detection. And so I took a job at Los Alamos National Lab. And within the first few years that I was there, we had these two incidents back to back. There was a security incident and there was a safety incident. And the director of the lab said, okay, everybody is stopping work. We're not doing any scientific work. Everything that we're going to do is based on, security and safety. And when we start doing scientific work again, it's going to be starting with the most simple work. We're going to start, with computer work. And I was in a group that did some of the more complicated, dangerous measurements using, nuclear material. So we were allowed to start doing computer work. And I went to my mentor at the time and I said to him, suggest to me something that I can do on the computer something technical or I will lose my mind. And he said to me, well, these detectors, they measure these signals, and they're one-dimensional signals usually. And in particular, we were looking at the signals associated with gamma ray spectroscopy. So gamma ray spectroscopy provides a unique fingerprint of the nuclear material you're looking at. He said to me, well, I've always wanted to analyze gamma ray spectra with wavelets. And I thought, okay, wavelets. Some professor at one point gave me a free book about wavelets. I've heard of wavelets, so I'm going to go read this book now. And I started getting into it, and it really kind of led me down this path of signal processing. And, it might not be recognized today as data science, but in fact, wavelets are the mathematical basis for the convolutional neural networks of today. So while it was not coined yet, this term data science, it was actually the very backbone and the mathematical beginnings of what became data science. And then I got just super interested in it, and here we are today.
That's fascinating. Do you find it interesting? I'm assuming, based on my very preliminary undergrad knowledge, that there would be mixed signals, there would be noise in the signals that you're picking from the environment, and I'm assuming the processing would have gotten much easier now if you were to just look back compare.
Yeah, so there is always a whole bunch of noise in the signal. Unfortunately, in the field of radiation detection, we are benefited by the fact that noise is well understood. It's Poissonian noise. It's Gaussian signals. So we can easily mathematically describe that. But what's harder to describe, that's the statistics associated with the source. But there's always background as well. There's background all around us, radiation background. A lot of people don't realize that, but even just sitting here in my house, the dirt provides me some sort of radiation background. There's materials in that, such as radioactive isotopes of potassium and thorium, and radium. Those are always there. And when we fly in an airplane, there's cosmic background. So we're always exposed to a radiation background. And while I can characterize what's happening with a radioactive source based on Poissonian or Gaussian statistics, it's harder to understand what it is due to background. But it fluctuates based on the position on the Earth. Some places are more naturally radioactive than others. It fluctuates based on the weather. And so characterizing those fluctuations is much harder. And so that was one of the reasons that we got my research group. After Los Alamos, for a while, I was a professor at the University of Illinois, and we started looking at sensor networks. And by this point, I started there in 2012, and the term data science and big data, those terms had already been coined. And so we're looking at these sensor networks ingesting fairly substantial quantities of data and trying to understand, were we truly at a detectable limit above background when background is fluctuating? So it's a much more interesting mathematical problem.
I understood a few of the terms you mentioned, but I've always been fascinated by radiation in general. Zooming out, if I may ask a broad question, since you worked in both, what's the meaning of engineering to you, and what's the meaning of research to you, broadly speaking?
Broadly speaking. So I'll tackle the research one first. Okay. To me, research is the stuff that hasn't been done yet. And that can mean a lot of things, of course. If you're talking to a scientist, research is the stuff that has not been studied in the peer-reviewed literature. So, it's not been published yet. So that's probably considered like research in its purest form. However, you can go to an opposite extreme and talk, you can be talking to a company in Silicon Valley or whatnot, some sort of tech company. And to them, research is the company hasn't done it yet. Go find something that's novel to the company. So the word novel here, I think, is what is consistent among both of these things. It's something new to the audience that's receiving it. Engineering, to me, is, let's take this thing, whether this thing is research or some sort of theoretical concept or whatever, and we're going to build it. And that can involve building a bridge or some sort of structure, or that can be writing code. So how do I take this novel concept and turn it into actual practice? That's where I see the two as being.
That really shines a light on the importance of both discovering what's the unknown and then building a bridge to actually bring it into the hands of everyone in a way.
Yeah.
I really enjoyed your blog on your transition into into the industry. Do you have any tips for people who are in a similar position today? Because one thing I've learned is people in the industry don't really care as much about what researchers care about, and vice versa. Maybe I'm wrong, but any
Oh no,
thoughts
it's
there?
very true. It's very true. It's um, coming as a professor, and people come from different portions of academia. You could be coming straight out of a bachelor's degree, a master's degree, a PhD, or a postdoc. Or in my case, I came out of being a tenure track professor, which is probably less common than the others. But there is this idea when you're doing research that you are a mile deep, is a kilometer deep and a centimeter wide. Whereas if you're actually a practitioner, you need to be a kilometer wide and a centimeter deep. You need to be able to do a lot of things. Unless you're working as, if you're working in Google or Facebook or Apple or one of these places where they have research scientists that they've hired. And so trying to understand how to go from deep to broad is hard. And so researchers, they think, I know this one thing, I know it really well, and everything looks like that thing. And I've written all these papers on it, and these papers are very important, and everybody's read these papers. And in reality, the hardest thing about transitioning from being a professor to being a data scientist was, I'm just going to say it, nobody cares. So I had this glorious curriculum vitae, CV, and then all these people said, "Oh, send me your CV," and I mean, it was like 20 pages long. And they're like, no, that's not what I mean. I want one page. And I was like, no, that's called a resume, not a CV. So there was some language, the vocabulary differences here. And then, oh, but look at these papers that I've published. No, those don't matter to us. So just getting out of that mentality that peer-reviewed publications are what matters into give me code that I can put into production. And then I'd write code and they're like, okay, well, that looks like a researcher who doesn't care, So there were growing pains involved.
How was the learning curve for you in the transition? As you mentioned, there was a difference that you were getting accustomed to. Any other points that really stood out?
Yes, the learning curve was steep and unpleasant. So I originally, when I was truly learning how to do data science, I got into a boot camp. And it was a boot camp, they said designed around taking academics and turning them into data scientists. And they were talking mostly about postdocs or people coming up on their PhDs. And the thing that I learned the hard way was I thought I knew Python. I didn't know Python. like I thought I knew how to program. I've been programming since 1979. Okay, I didn't know how to program.
Python didn't
Just
even exist at that point.
no,
I'd just like to point
it's
that out.
true. When I first learned to program, it was basic, and I'm not talking Visual Basic. I'm talking basic. And after basic, I learned what did I learn? Fortran 77, and I did Fortran 77 for many years. That was and continues to somewhat be the language of physics. And after I learned Fortran 77, I got to Los Alamos let's say I started there in 2002, and I learned C. Okay. I missed the whole Java thing. Java happened, and I was not in school. And then all of a sudden, here's Java, and I'm like, oh, I got nothing here, and JavaScript, and and then I just said, okay, I'm just going to forget those things. I'm just going to go straight to Python. So, and then I learned Scala, which I love, but yeah, it was hard. It was a hard realization that I did not truly understand how to program when I'd been doing it for decades. And I'll tell you, I'm still not a good programmer. I mean, I think everybody who's been programming for a while says they're still learning to program. And I definitely consider that. So that was a really hard thing with the boot camp in particular.
I can only imagine. And even though you've programmed in languages that I would call are much harder than Python to grasp, I'm sure it was a learning curve.
It was. Compiled languages, I mean, just such a different different game.
Right. So transitioning into Neo4j, I'd love to talk about that. For the listeners, I'm going to share my screen, but if you could just talk about what Neo4j is and what's it all about.
Yeah, so Neo4j started as a graph database company. And the idea being, those of us who work with databases, like perhaps a lot of your listeners are coming at the world from a SQL database idea or a relational database where I can have a table and I've got columns and rows in the table. And in the data science world and machine learning, we like to think about our data. Each row has no relationship to the next row. Each row is an independent data point. In reality, most of our data isn't that way. Most of our data has relationships to each other. We think about social networks. That's a very common example. And the power of understanding how each of our data points relates to each other. I'll use an example here, which is churn. How can we come up with a mathematical model to predict which of our users are going to drop off our platform or cancel their account? Very common data science problem. And you can solve this problem using a relational database, and that's great. But if you think about, say, like Facebook or something like this, these data points relate to each other. So, you and I might have a friendship on Facebook. If you decide to leave Facebook, my probability of leaving Facebook myself just went up by a lot just because one of my friends has left. So, one of the great things about a graph database such as Neo4j is that it treats those relationships as first-class citizens. It says, we're not going to treat these rows and in our tables as being unrelated to each other. We're not going to have tables. One of the things that people ask me is, well, how do I know I have, I'll put this word in quotes, a graphy problem? What's a problem that really should be represented as a graph? If you're somebody who works with tables, SQL, what otherwise, pandas, something like this, and you find yourself having to do more than a few joins, you're probably talking about a graph. And the problem can be solved more efficiently, faster, and easier with a graph. So Neo4j is a company that puts that technology in your hands. It's organized its data in a form such that you can do these graph traversals very, very quickly. I did a comparison once where I did some ugly SQL query. And then I compared it to the identical query within Neo4j. And in SQL, I want to say, it took like 2 seconds to complete. And in Neo4j, the very same query took 2 microseconds to complete. So it's orders of magnitude faster.
Fascinating. Just off the top of your head, many people use simple join in pandas or whatever they use for tabular data. Do you think they would be a speed up if they were just to switch to a graph based solution? And for the listeners, graph refers to the data structure, which I almost don't remember. I had almost failed that exam. But
Yeah, it's funny because I told my mother I was going to go work for this graph database company. She says, I don't understand. You've got an axis that goes this way and an axis that goes that way, and you've got a line. What's the big deal? And I'm like, no, Mom, it's a little more than that. So yeah, it's when you start talking about doing joins with pandas. One join probably is not going to make the difference, but if you find yourself doing a handful of joins, you absolutely will notice a difference. And, especially you think about like some of the more basic questions that get asked in software engineer interviews, data science interviews. They ask questions, write me an algorithm for depth first search or breadth first search. It's trivial in a graph database, absolutely trivial.
yeah.
Pandas, if you want to write that in pandas, you're going to be sitting there writing a lot of lines of code. And a lot of lines of code don't run fast.
So for people who are just trying to explore this as an option, I'm assuming a few of the listeners, how much of a difference would they feel? Because most of us are just used to reading as CSVs and not working with Dijkstra algorithm or just traversing graphs.
Yeah.
If you could just talk about that.
I'll tell you right now, if you're doing something in pandas and you take it to a graph database and you do not see a few orders of magnitude improvement, don't bother. But I'm pretty confident in saying if you're working in pandas and you're doing these joins, you're going to see a speed improvement. The other thing I'll say is that, when we're doing stuff in pandas and we're, doing some sort of exploratory data analysis, or we're trying to generate a machine learning model, we can get much better results, whether you want to measure better as accuracy or F1 score, pick your favorite metric, if you consider those relationships between the data points. So it's not just enough to say what's my improvement in speed, but also what's the improvement in the accuracy of my model.
Gotcha. I'm going to share my screen again for people listening into the audio. I'm just going to speak out about the products, but I'm looking at the page, and if you could help us understand what all of the products are here for. I assume Aura and Bloom are different versions of the library to handle different parts of the
Right.
problem.
So let's start at the top there. The Neo4j graph database, that's the bread and butter. That's what we do. And then you have in there, you had Bloom was next. Bloom is a nice visualization. It's Aura next. I apologize. Aura is our self-hosted solution. So this is you get an Aura account and you click a button, and all of a sudden you have a graph database created for you, living in the cloud. You don't have to do any kind of configuration. It just works. And you can say, okay, well, I have, I need this much memory, and I expect to do this type of things with the graph. It'll help you configure it. But the great thing about it, especially from a data science perspective, I'm not an infra person. I'm not a data engineer. And I can tell you the majority of companies that I have talked to, they say, okay, let's hire a bunch of data scientists, because everybody's hiring data scientists, but they're not hiring the data engineers. So the data scientists get there and they say, okay, great. What's our infrastructure? And the answer is, and so then it's like, well, go make it. Well, data scientists aren't infrastructure people. There's a reason data engineers are who they are. And we cannot have enough data engineers. You really should hire the data engineers before you hire the data scientists. Get that infra in place before you get the people who need to start hitting at it. So Aura is great because you, as a data scientist, you just click a button and spin up an instance. You don't have to worry about that infrastructure thing. So it gets you from, some sort of, well, I need to do some EDA on this data, to a full-on proof of concept much, much faster. The next thing on that list was Bloom. And Bloom is really a nice analytics tool. It gives you a good visualization thing. It allows you to explore your data in a very efficient, easy to understand fashion. You'll see that box in the middle there, Bloom Sandbox. We've got things here where people can experiment with all of this stuff for free. Okay, so Bloom Sandbox is a great way to get started learning Bloom. If you configure it, it'll walk you through these whole steps, and it'll populate graphs for you, so you don't even have to worry about that part. After Bloom, my favorite, the Neo4j Graph Data Science Library. Okay,
And
this is
just to point out, this also has a Python API, and it's up for download on the website as well, if I understand
That's
correctly.
correct. Yeah, all of this stuff is available for download. There's free versions of all of this, and all of it has a Python API. Or, you can use Java or JavaScript or Go. GraphQL is one of our latest fun things. But yes, so from the data scientist perspective, Python, we do have a Python driver that is officially supported. And then there's also community drivers out there if you prefer those. But the Graph Data Science Library is really where I think your listeners are going to get the most interest in the bang for their buck. So the question is, okay, I've got this graph. I can query the graph just like I can query SQL, but there's so much more that you can do, and it's all enabled by data science. So, we look at, you can see here on the screen, there are kind of these 6 main pillars of the GDS library: community detection, centrality, etc. And what this is, okay, I can, as a data scientist, as a machine learning engineer, I want to create a model. I want to calculate something based on my data set. So my model will involve features, and maybe I spend a lot of time doing my feature engineering, or maybe I can somehow vectorize my data. I can create this embedding. What Neo4j does is it does that for you. So you can create those vectors yourself through the GDS library, and then you can do anything you want with them. And here's 6 instances where we can use the GDS library to solve really interesting data science problems that are
I'm sorry,
beyond just simple
GDS,
queries. Oh,
just for
sorry,
the
graph
audience,
data
stands for
science.
graph data science.
Yeah, graph data science. Sorry, I just blow through that acronym. It just kind of rolls. But yeah, so we've got these built-in things that do a lot of data science for you. And then, as if that's not enough, we do have some built-in machine learning functions. 2 of the big things that people want to do from a machine learning perspective with a graph are node classification and link prediction. I've got this unknown entity within my graph. What is it? Can I predict what it is based on everything else around it in the graph? And then there's the link prediction idea of, okay, I've got these 2 nodes, and what's the probability they have a connection between the 2 of them? So those are built in as well within the GDS library. Speaking as somebody who comes from a machine learning background, I like to take it to the next step. I like to use those embeddings myself. So I can use Python. I calculate the embeddings within Neo4j. It's very fast. And then I suck those embeddings down with Python, and then I can run them through whatever machine learning algorithm I want. So I could be running TensorFlow or scikit-learn, PyTorch, whatever is your favorite. It's just a list of numbers. And that's what we do as data scientists. We create a list of numbers, we develop a model out of it, and we measure, the performance of that model. So the same idea applies. It's just that you're vectorizing a graph instead of individual data points.
Zooming out, I think at least the use case we learn in undergrad is this is used in social networks a lot, like you mentioned, just because it's so easy to connect different profiles via graph. You can have 2 nodes that you can traverse, so on and so forth. But on the website, there are different use cases. And if you'd just like to talk about a few or one that's your favorite that this enables.
Right. So lately so fraud detection is always a great one. This is where graphs truly shine, because if you start getting into fraud detection, this is a complicated problem in data science because you have a huge class imbalance. You have so many more data points that are not fraudulent versus those that are fraudulent. And setting up a model around something with that huge of a class imbalance is very difficult. But it's with Neo4j or with any graph database, you pull that up into a graph, maybe you're using a visualization engine like Bloom, and it just jumps out at you. You're like, aha. You may not even realize what the important feature is of the graph, but you can, when you see it, it just jumps out at you. So that's one that I like a lot. One of them that's not on here, I don't think it's on here. If you scroll down, I could tell you, maybe they updated the webpage. Knowledge graphs. I love working with knowledge graphs. And the idea here is, there it is. Yay.
It is
okay.
there.
Oh, good. I'm embarrassed to say when was the last time I looked at that particular webpage. Knowledge graphs, that's kind of like the backbone of what is Google today. So how can I link bits of information? Maybe it's coming from completely unstructured text. Maybe it's Wikidata, which is fairly structured. Maybe I am, maybe I'm a lawyer. I work within some very large law firm, and I've got thousands upon millions of pages that are text. How do I get information out of that? I want to be able to ask questions of my data. I want to be able to say, how likely is it that this one legal review is related to this other law case? And knowledge graphs do that for you. And that link prediction that I just mentioned, what's the likelihood of this legal review being associated with this law case? That's all machine learning on knowledge graphs. So that's a particular favorite problem of mine right now. I personally really enjoy doing natural language processing to create knowledge graphs. So if you were to attend, we have an upcoming event called Nodes, which is Neo4j's tech event. And the week before Nodes, I'm actually giving a workshop on how to do that. But there's actually several talks at Nodes on knowledge graphs and how to create them. So really, really hot topic.
The audience know I'm very bad at editing, so if I these this episode comes out late, I'll have the links that I think will still remain up, and you can go still check it out in case I take too
Cool.
long to edit, which most of the times I do.
Well, we will have videos out there, so watch on YouTube. It'll be showing up.
Awesome. Zooming out, your job title is Graph Data Science Advocate. I'm sold on Graph Data Science. I'm going to give it a try. Maybe put some content out there as well. But what does your day to day at Neo4j look like, and what tasks are you involved in? Are you involved in the dev side of things as well, or?
So where I fall is under the developer relations team, and so really my job is as an advocate. And I view that as being a few different things. And this is one of the things I really like about my job is it's very different day to day. My job is to be out there kind of talking to data scientists and talking about the power of graphs, showing them when you have that so-called graphy problem, and why can we get a lot better results by treating a problem as a graph rather than as a table. And as we go along this journey, the journey that I took, this started when I was really at GitHub in earnest. I had graduate students working with me and postdocs working with me who started me on this idea of, graphs, that might be useful someday. But when I was at GitHub, that's where this thinking really got going for me. And so I started, okay, there's this concept of a graph. Cool. And then people like myself tend to say, okay, I want to do graphs in Python. And they find this Python package called NetworkX. Pretty common package that's out there. A lot of people use NetworkX. And it's like, okay, cool, NetworkX, I get it. This makes sense. And then you start getting into data that's large. And you start realizing, oh, shoot, I cannot get NetworkX to complete this calculation. It will not converge. NetworkX just doesn't scale very well. And then that takes me into a graph database. And I'd explored several of them. And I obviously even before I came on board Neo4j, I personally preferred Neo4j. And so my role is, can I take that data scientist, who knows data science, may not realize that they've got that graph problem, and help them along this journey, and hopefully make it less painful than mine was, more efficient and smoother than mine was, by showing them, hey, check out this tool here. We can skip over some of these steps if we just understand what is your data? How big is your data? What kind of things do you want to get out of it? And help just facilitate that thought process. So what that all comes down to is a lot of my job is going out and networking with people and talking with people at conferences and meetups. That's obviously hard given the state of the world right now. But I didn't even hire on to Neo4j until January. So, I hired on during the pandemic, so that's made it a little more complicated. But then I also do a lot of writing of blog posts and developer guides. So sorry about my dog in the background here.
Totally fine.
But yeah, so I spend time developing blog posts on, mostly I publish in towards data science. But there's a developer guide or two out there with my name on it on the Neo4j webpage. It actually doesn't have my name on it. We don't put our names on the dev guides. But so my job is to, as my boss put it, make cool stuff with graphs. He didn't say stuff, but I'll say it, make cool stuff with graphs and go out and talk about it.
Awesome. Zooming out, I also read a blog, I think by you, that was titled around working from home. So I'm kind of struggling with it. Like I'm an introvert person by default, but I kind of miss also meeting people and sometimes feel burnt out. So what's your best advice to people who are still struggling with it? I'm assuming a lot would have gotten better. I'm not one of them.
Yeah. Well, okay. So I have been working remotely since 2017. So for me, this was not new, the concept of working at home. But I still like meeting with people. I still like that three-dimensional interaction of being able to go to a conference or a meetup and just to sit down at a whiteboard or get a cup of coffee or a beer or something and just talk to people. What you working on?
Yeah.
What problems are you encountering in that? And so that's hard. But I really, having worked from home, it was an adjustment. When I started in 2017. So we have the pandemic hit and everybody starts working from home in 2020. And I felt really bad for those people because, this is the impression people are getting of what remote work is like. And it truly isn't. I was very fortunate that my first remote job with GitHub is a remote first company. When I hired on, I don't know what the numbers are now, but 70% of employees were remote. And so they really have a culture that's designed around that. So, for example, companies with good remote culture do things like, hey, you know what? Let's get you a proper chair for your desk. And like they did an ergonomic consultation. So I'm sitting here on Zoom with this ergonomics professional who I think was located in Oregon somewhere. I don't remember exactly, but certainly not sitting there with me. And we're on Zoom and she's like, okay, I want you to now back the computer up because I want to see how where are your arms and where's your back and all of this stuff. So, they paid for me to get a nice chair. And I have a nice sit stand desk here. And it really matters, that stuff. But then you look at the people who were thrown into this during the pandemic, and, the entire planet had this freak out. Nobody knew how to do this. So they just said, okay, everybody, we're leaving now. Take your laptop. Someday we'll be back. And, so you had people working at their kitchen counters, and they're all typing like this. And, of course, people's bodies take the fatigue of that. But then the mind also takes a fatigue too. So, the idea of pre-pandemic, remote work is about flexibility. So I can take my computer and I can go work out of a coffee shop, or I can go, work out of the library. I won't admit to having worked out of a bar before. I have been known, I am a big skier. I have been known to, I just need to clear my head. I'm going to go ski a few runs and I'm going to come back to it. That's not something you can do in an office. I'm going to go have lunch with somebody who I don't work with, just a friend. We're going to have lunch and it just gives me a chance to mentally take a break. And then I'm much more productive at that. And nobody had the chance to do that with COVID. So one of the things that I highly, highly recommend, if at all possible, is to find a way to separate personal life from work life. This is very important. And there's a few ways to do that. I think there's this tendency of, oh, I'm stuck at home. It's lockdown. I'm really bored. I might as well just work. You gotta shut down. If you were in the workplace, if you were in an office, like in a building that's not your house, you'd leave it. You leave your work.
Yeah.
And maybe it's still in your brain. Maybe you take your laptop home, but you leave that work. So being able to even just visual distance. I think of people in very small apartments and whatnot and small flats, but being able to have a space where you don't see the work. Even if that means you're in a very small place and you just have a desk that folds up and it hides the work. That's a mental cue that I'm not at work anymore. Shut down Slack. Shut down email. When you're gone, be gone. Set yourself, okay, if I'm done at 5:00, I'm done at 5:00. I'm not responding to emails. I'm not responding to Slack. One of the best things I've done, I've got my phone right here. Do not have the Slack app on your phone. Or if you do, and I get it. People are on call. This is totally different for people who are on call. Hide the app on the weekends. Just hide it. Don't have it on your main screen on your phone. So it's stuff like that. Setting up a space that you're comfortable in. It's not about, if you could avoid working at the kitchen table, do it. Just do it. So yeah, those are I think my biggest suggestions.
I assume other people would be smarter about this, but it's I think it comes with age. I don't really have an off button. Like I'm always trying to think about work, but then I'm also not, because in your blog post you mentioned you're not scrolling through Twitter, which I almost now do. Even at office, I would do it sometimes. I'm just scrolling through Twitter, and then the work hours feel longer than they should, and the
Yeah.
burnout enhances because I'm sort of constantly always thinking about work. And then even on weekends, like you mentioned, my phone, my iPad, my iWatch, everything goes off at the same time when Slack gives me a ping, and now I'm
And
getting
I mean,
anxiety.
there's that FOMO thing, fear of missing out. Ooh, what if that one ping was super important? What percentage of your pings are super important that really truly cannot wait until Monday, right? Um, I have this, people like lose their minds when I tell them this. I have this email thing that I do. I hate email like a lot. And I don't read it. I don't read email. And people are like, what do you mean you don't read email? How can you function without inbox zero? And I don't know. I mean, I could show you my inbox right now. I have, since hiring on at Neo, I have over 1,000 unread messages. And
Okay.
everybody's like, oh my gosh. What percentage of your email truly requires you to read it? You've got oh, here's the update from some team that really doesn't impact me. Somebody sent the calendar invite to, 500 people for coffee. Those
Yeah.
things don't matter. Your eyes, you're able to look at that subject line, and within less than a second, you can say, this is an email that's important to me. But the trick is, and this is the true trick, is you don't delete any of them. And I can just hear all of the IT people who might be listening to this. They're just screaming right now, oh my gosh, you're the reason why my mail server dies. If you have a good search engine associated with your email, I'm not going to mention what ones don't have a good search engine, Outlook, but let's take Gmail for example. Gmail, based on Google, a search platform first and foremost. So if somebody says to me, oh well, did you read that email 2 weeks ago about XYZ, I can go and I can find it because I have a good search engine within my email. But probably I would say greater than 75%, maybe even I ignore greater than 75% of the emails. So
I think we all need to learn about that at some point, to some extent.
inbox zero is a myth. It is an unachievable myth.
I would agree with that. But zooming out, I always end on this question of sorts. So, what's your best advice to someone who's just starting their journey? Maybe your students at University of Illinois would always ask this question to you. So, broadly speaking, what's your best advice to anyone interested
Ooh,
in data science?
ooh, that's a really good question. Okay, so a couple things. Do not ignore the math. If I had to do it all over again, I would take linear algebra about 50 times. Like, I was a horrible student. I was terrible. And linear algebra might have been my worst math course. And it is so foundational to what we do. Similar with statistics. If you had told me in the late 90s that statistics was going to be the hot major, you would have knocked me over with a feather. When I was at Illinois, you could not get into statistics classes because of data science, because of how booming the whole field was. So, do not ignore the math. But then the other thing I would say, and I would be in a lot of trouble with a lot of my former professor colleagues back in Illinois for saying this. Professors are great. They teach great subjects. They are what is going to give you that foundational knowledge, but they are not practitioners. So what I mean by that is that they can help you to a point. They can help you get exposed to the material, but by and large, and this is not 100% true, but by and large, they do not have industry experience. So they can talk about things much more from a research perspective, especially if you're talking about like an R1 university like the University of Illinois, but they do not know what it is to apply that stuff in the real world. And So you have to find that somewhere. And the best place to find that is through internships. Um, spend every summer possible working with anybody that you can. And if you can't get an internship, be constantly working on projects to build your portfolio and just demonstrate, that you have skills beyond just what's in the classroom. You can take that data, and it's go get some data off of your favorite subject. Get it off of Kaggle, get it off of some of the open data sites. Google has a whole bunch of data. Kaggle is it's better than nothing, but that data is pretty clean. But just go scrape the web. Scraping the web in and of itself will teach you about how messy data is. I would guesstimate 85% of my job is not actually doing data science. It's acting as a data janitor. It's cleaning, it's collecting, it's scraping, it's cleaning and cleaning some more and cleaning some more. And when you think you're done, you clean it 500 times more. And even just demonstrating that you can clean data is hugely, hugely useful. But get that data set and then do something with it. Pick a project, pick a data set of a subject that you're passionate about, and go find some data on it. And if you can't find it, make it by scraping it and do something with it. Clean it, make a model out of it, write a report out of it, and describe it. You have to be able to communicate as a data scientist. So don't just write code. If you're going to use a Jupyter notebook, awesome. Every cell, you should have between every cell of code should be a comment cell describing, here's what this next cell is about. So literally half of your cells should be comment cells. Just demonstrating that you can walk somebody through this. If you're writing just straight old Python, doc strings and more doc strings. And do not assume, I know people who their view is, if I have to comment my code, that means you're not smart enough to understand it. And that just, I find that offensive, frankly. I'm not a smart person, and I still think that if you can't comment in your code, you're not a smart person. Type hinting, like people didn't type hint 10 years ago. Oh my gosh, is that massively useful now, right? So being able to say, this is what my code does, this is why it's important, this is what each function does, this is what each class is for. Just people seeing that you can talk as a human being about what's a massively technical subject, that just goes so far. So I don't know, that's a really long-winded answer to what I would suggest.
I love the term data janitor, but respectfully pushing back on your advice,
Yeah.
I'm from the school of top-down learning, where it's advised to just dive into stuff first. And then there's also this FOMO that I always feel, hey, maybe I should take that linear algebra course, maybe I should take that stats course, which really pulls me back from actually building stuff, or just scraping the web and
Yes.
building projects. So how much of a balance should there be, and how should we find that balance? Because again, these are different rabbit holes to explore.
That's right. And I think the problem is that we assume that it's an either or. You can either come at this from a formal educational perspective, the bottoms up perspective, or like you said, the top down perspective. And I think both are valuable. And what's the right blend? I couldn't tell you. I think it's different for everybody. For me, most of my work has been from the top down perspective, throw you into the deep end, sink or swim. And I find myself regretting that I didn't have some of the more foundational stuff in my learning. And yet I talk to people on the opposite spectrum that, I wish I could have just gotten right into it from the get-go. Both. Do both.
Gotcha. I have a few short rapid fire questions. Usually it's not
For
a
sure.
rapid fire that I'd like to ask. What's your favorite spot to ski?
Oh, my favorite skiing sport?
Yes.
Like,
No,
oh my gosh.
spot to ski. I mean location.
Oh, my favorite spot to ski. Well, I live 5 miles from Breckenridge. Breckenridge ski. So I kind of have a bias there. My husband works on the hill. I'm a retired ski patroller, not from there, but if I had to actually pick one that I don't live nearby, and in fact, this is my Ooh, wait a second. No. I love skiing snowmass in the Aspen area, but I also, I've skied in the Alps in Chamonix in France, and well, it's where France and Italy and Switzerland come together. And that's just such a different environment. It's almost hard to call it skiing. It's like skiing on a different plane of existence. So I like all those areas.
Awesome. In your previous life, you were at GitHub. If you could just talk about anything that really stood out to you while analyzing all of these repositories that you could talk about.
Yeah. So this was actually one of my bigger introductions to graphs while I was at GitHub. And so the product manager came to us, and I was on the machine learning team, which was a brand new team when I hired on. And he said, we really need a tool that can try and find duplicate code. So there's this estimate, and it blew my mind, and I'm not going to be able to pull the number out of my mind right now, but it was something like greater than 80% of Java on GitHub is duplicate. So, for example, let's say that you and I are both in a class, and we're in a class on Java, and we've each been asked to write a function to calculate cosine. Okay. There's a handful of ways that you can calculate cosine, but it's fairly limited, right? And so we both calculate cosine, and maybe you call your variables x and y. Maybe I call my variables I and j, whatever. It's still the same function. And so the idea would be is that, I am calculating cosine, and GitHub detects that I'm trying to calculate cosine, and they say, oh, you know what? Sanyam has this code that he used. Maybe we can help you write some code here. Or the nefarious side being somebody is, leaving a company and they're not happy about it. They're disgruntled about it. And they go and they steal the company's repo and they go post it as their own work someplace else. That'd be bad. So detecting duplicate code is, it's kind of an important problem. And not only that, but let's detect duplicate code across languages. Or even across methods. You use one method to calculate cosine, I use a different method. But let's say you are writing cosine in Java, and I'm writing it in Go. Okay. Complicated, right?
Yeah.
How can we tell that those are actually the same bits of code? So what we did is we were looking at the abstract syntax tree, which is what a compiler truly looks at. Compilers don't really care about much other than this thing connects to this other thing. So this function connects to this variable, which connects to this return statement, so these abstract syntax trees are graphs. They're tree graphs, but they're graphs. And when you talk about graphs, one of the ways that you can represent them is as a matrix called the adjacency matrix. And it's just showing in rows and columns which elements are connecting to which other elements. So one of the more fun things that I did during my time at GitHub was we had a data set of Java code that was labeled. It was a lot of code. It was at the function level, it was at the file level, and it was labeled as whether it was a duplicate to something else or not. So it was actually a supervised machine learning problem, which that's more rare than I think people realize that you get a supervised problem. And so we created, we took the adjacency matrix, which this looks like, just columns and rows of ones and zeros. And to me, coming from my astrophysics background, I'm like, oh, well, that's an image. Okay, so now I got an image. Well, now that means I can do some convolutional neural nets. Is this a cat or is this a dog? Okay, is this a duplicate or is this not a duplicate? And it turned out we could get amazing accuracy on these wildly different, if you looked at these adjacency matrices as images, you look at this image, you're like, oh my gosh, how do you tell that's a duplicate? Well, the model can. And, we were getting something like 97% accuracy in our ability to detect duplicate code. So that I thought was really super fun. I loved that project.
What I'm worried about there is students would understand that's how we cheat around in assignments. You just change the variable names and you get away with it. And if this tech is out there, they wouldn't be able to do that.
Yeah, it's sad but true. However, I will say that, the plagiarism detection engines are getting slowly better. slowly. Having been on the receiving end of that, I always taught lab courses, and, I'd get this lengthy report of, here's all the students that are, copying each other. And it was ridiculous stuff. Like, oh, look, these two students named their axis the same thing, energy. Well, of course it's energy. That's what we all call it, So like to wade through that stuff was just ridiculous. So if there's any of your listeners out there who are looking for a great project to demonstrate, put in their portfolio, this would be a great one.
Awesome advice. I just doing my research for this interview, research quote unquote. I learned, and I'm sure as the audience would have observed, that you're a great speaker in general. What's your best advice to people who are trying to improve on it and still trying to improve on it?
Practice, 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 practice. So for me, I come from a theater background. I did a lot of theater as a kid and growing up. And so I learned performance, and people are like, oh, well, that's too artistic, but it doesn't have to be theater. Putting yourself out there in front of people, a musician, if you go perform places. And it is about putting yourself out there, but also realizing that the audience is not out to get you. The audience wants you to succeed. They want you to give a presentation that helps raise their awareness to a thing, that inspires them to a thing. They're not out there to attack you. And I think that's kind of the default mindset of people who get nervous going in and speaking. There's always the question that we fear in the back of our head. Oh, please don't let somebody ask me this. And this is something that I would talk to my graduate students about a lot. We all have that question. There's always that one question that you do not want to be asked. And the psychology is such that somebody will ask a question, and it'll be worded in a way such that you don't necessarily understand what's being asked. And your brain defaults to going back to that question that you're dreading. And that's usually not what they're asking. And so clarifying the question before you answer it is so important. But then also the power of saying, I don't know. And usually it's better to say, I don't know, but I will find out and get back to you. But don't make it up. People can tell when you're making it up. And yet if you say, I don't know, then they feel that they've gotten an honest response from you. They will automatically like you for having given them that honest, I don't know. Come talk to me afterwards. I'd love to get your contact information and we can follow up on this. That's like, so even if you get that one question you're dreading, there's your response right there.
That's awesome advice. And just to speak on your point of practice, I'm just holding up my empty chai cup, which I've just drank through. This hand would shake a lot during the early days of the podcast, and that has gone away. Even on Zoom, at least I would get these shakes when I'm sipping water or just drinking chai, and that has gone away with practice.
But that's to your advantage, because the reason that we shake is because our adrenaline level is very high, right? We're nervous, our adrenaline level goes up, our cortisol level goes up. Take that and use that, channel that. That gives you energy on, at the podium, on the stage, in the Zoom call. And that energy makes people want to listen and excited to listen. So the fact that your hand is shaking is a good sign. Use it.
That's awesome advice. I think I've gone through all of the questions that I had for you. But before we end the interview, you're on LinkedIn and Twitter as well. Any other platforms where the listeners can connect with you?
Those are the Twitter in particular is the best one. So I'm CJ Loves Data 1 on Twitter, but you can also find me on GitHub. So on GitHub, I'm CJ 2001. And I've got links to my blog posts and several of my talks on there, including some of my more recent talks. But that one about the duplicate code, there's a talk on there, linked out there as well. So if anybody's super interested on that, it's there.
Awesome. Again, as a reminder, find these links in the description in case you missed out on them. Claire, thank you so much again for your time and for such an interesting interview.
All right. Thank you.
Thank you so much for listening to this episode. If you enjoyed the show, please be sure to give it a review or feel free to shoot me a message. You can find all of the social media links in the description. If you like the show, Please subscribe and tune in each week to Chai Time Data Science.